Okay, welcome everybody, and so let's start the session. My name is Paweł Kamiński. I'm working for CodeWise here in Krakow, and today I would like to tell you, if I find the pointer, I would like to tell you about the small and simple library called Stardust that we created after having some problems with communication between microservices. And so the story is about not getting stuck on the highway, and let's get started. So I would like to first guide you through some background and who we are, CodeWise, what DSP team does. And I don't want to get into details, but this will give you some intuition what we are doing and what kind of problems we're dealing with. And so probably you all heard about microservices, and you would like to use microservices because you want to, I don't know, mirror your organization hierarchy. Maybe you want to scale services independently. You would like to allow different lifecycle of different services. Maybe you would like to allow different coding style or maybe technology stack. Maybe you would like to define some fallback scenarios when facing failures. And the probably most important, you want to hide complexity and define clear interfaces between services, so you can change and maintain the whole application easier. So that's the basic, and I guess it's microservices are very popular now, so I don't really think nobody knows anything about the microservices. So what's the DSP? DSP stands for Demand Side Platform, and we perform online real-time bidding, and we are connecting the ad consumers like you with the advertisers, and the so-called SSP are sending us requests, and they are demanding the ad, and we have to choose the best ad and send it back so it can be displayed on your device. So everything started, at least for me, in 2015 with 3 other people. We created the DSP team, and the goal was simple: to process 1 million requests per second, and each request is supposed to be processed within 100 milliseconds. So at that time, it was very, very challenging for us. Although we have some experience, that was like a new level of complexity, and we were really eager to start working on this project. And this is the simplified sketch of our architecture at that time in 2015, and probably it looks like this for some time. And as you can see, there is like 2 different sides of this picture. So the upper side is so-called fast path, and below there are services that are not that important. They don't have to have that performance. And okay, so at the top you can see the first layer that is internet facing. We call it traffics, and traffics are responsible for decoding and encoding JSON payloads. They are also responsible for enriching those payloads, so we get all the data we need to process them. And the second layer is the bidder layer. So bidders are the core service that have all logic that is needed to decide whether we want to bid on the request or not, and what we should respond. And the companion service, wallet, it's dealing with the transaction, and so it makes sure that we are not overspending client's balance. So I think that it won't be something bold if I say that at the time we had some experience with microservices. We knew how to log, we knew how to debug, we knew how to automate stuff, and we had experience with Amazon Cloud. So the only thing that was left to figure out was how to connect those services on the fast path, so to cope with the given requirements. A no-brainer that we want to have binary protocols on top of the long-living connections. We wanted to apply circuit breakers. We want to have some discovery mechanism and route the traffic internally by ourselves. But also we relied on the asynchronous non-blocking socket implementation, and that seemed to be a right choice. And we've chosen netty IO, and because it promised a lot of things like separation of concern, of non-blocking and blocking socket implementation, about good thread models, but basically we saw a lot of good benchmarks that showed that netty will deliver those promises. So let's have a look. I don't know how many of you used netty before. So I will just guide you so we are on the same page and you understand how netty works. Netty has various types of builders you can use, and we have to just define which thread group is going to accept connection, which thread group will execute requests within the connection. We can choose the socket implementation. We can decide what to do on each connection that is created, that is accepted. And of course, we can define what steps are going to be executed for each request. So it's very basic. I think it's very intuitive, and it looks really good. The client is very similar. So again, you need to pass some thread group and define your pipeline. Handler. It's also very simple. It's like a unit of work in the pipeline, and you need to just extend some implementation of handler. Handler can also understand your domain models. So it's not only about transforming raw bytes. You can actually very quickly transform from bytes to your domain model and then to use this for better abstraction. And netty for each request will give you the context, and with the context you can decide whether you want to push data, transform data to next handler in the pipeline, or maybe you want to write something back. So that's very important for me, and that's why I would like to go again how this works. So you have the vocabulary, you have the idea. Here you have like 3 connections, 3 channels. We have a pipeline, and we have 2 event loops that forms a event loop group. So a pipeline is just a chain of steps, a chain of handlers that are executed for every request. And event loop is just a thread with a fixed lifecycle, and other threads can interact with this event loop only through specialized queue. And one event loop can own 1 or more channel, and the channel represents a connection. It's always controlled by same and only one thread event loop, and it references the pipeline. So we have all coming together. We have connection, pipeline, and thread that controls it. Here, I'll go quickly how the event loop works. So we have the queue I mentioned. I have the orange thread, and I have the pipeline buffer and the separate event loop that will interact with wants to do something on this connection. If there's something in the buffer, the owning thread will pull it up and pass it to the first handler in the pipeline, and it will execute this pipeline and get some result and push it back to the client, to the caller. And if it's done, it will realize that the other threads push some tasks to the queue, and it will pull those tasks and execute them. So those tasks can be also interact with the channel, with the connection, or they can just do some basic work. And now the orange threaded event loop is idle, and if there's again something in the buffer, it will execute the whole process again and again. That's why it's called event loop. Let's have a look at some benchmarks, because that's interesting. So that's the benchmark I created some time ago, and this is run in the Amazon environment, in the same availability zone. We have 10 gigabit internet between those machines. We have 4 cores, 8 gigabyte of RAM, and I wanted to design the benchmark so it mimics real workload. So server is actually doing something. It's not only receiving and echoing the request. It's processing the request and sending unique reply. And so here we have a client that is only one client on the one machine that creates only one connection, and this one connection is backed by one thread, by one event loop, and the same on the server. There is only the server is accepting the connection by one thread, and I was able to push 10 million messages within 16 seconds. So it's around 600,000 messages per second, which is impressive. And if we look at the histogram of the response times, you'll see that majority of the responses were back within 1 millisecond. So it's very good result. And I wanted to see how netty scales, and so we can use the resources we have. I mentioned that was run on the 4 cores machine, so let's have a 4 connection backed by 4 event loops on the client and on the server. And this time, if you not realize, each event loop will send only 2.5 million, but in total we will send 10 million messages. And as I state here, I was able to do this in almost 9 seconds. So it's around 1 million requests per second. And as I proved that netty has these capabilities, and it was a good decision, right? Again, I plot the histogram of the latencies. It's not that perfect as in the first scenario, but if you compare first scenario to the second one, it's not that bad. Although of course there are the latency in the second scenarios are worse. So let's get back to the business. Even though I proved that netty does the job, let's get to the problem, right? Get to the topic of this speak. And in 2015, we have very basic architecture. We had only 2 main services on the fast path. But at some point, we realized that we cannot squeeze all data needed in bidders in order to reply to the caller, and we introduced specialized services. And each of these services holds the various information that it's needed to make decision whether we want to process this request or not. And we have services with blacklist, we have services with whitelist, IP list, fraud list, how frequent that was displayed, optimization services, loyalty groups, and many others. So we had like 10, we had to make 10 async calls from bidders in order to generate response. And we still had to respond within 100 milliseconds for each request, right? So for me it was, it's crazy. And it would be good, but we had one simple problem. And the problem is that we stopped processing, and we didn't realize at the beginning what's actually going on. And but our secret breakers, they trigger and they closed all the communication. But not only on the traffic layer, as you can imagine, but also on the bidders layer. And it's not only timeouts, but all different sort of errors. And you may now think that it must be a performance of one of those specialized services, of those downstream services, that causing this increase in latency, and that's causing the closing of the circuits, right? But actually, that was not the case. We tested each of those services with some performance tests, and we showed that we have no problem. So each of the individually, each service were performing very, very well under the heavy load. So what's the reason? If you remember this slide, and everything with netty performed really well if there is no asynchronous job to perform between those steps. And as asynchronous job, I mean, for example, client communication to downstream from bidder, for example, to one of those specialized services. And if you while you're configuring the client, netty demands the event loop group, the thread pool that will execute client's pipeline, and probably you can make a lot of decisions here, but you don't want to create the connection for new connection for each request, because it's just a waste of time. So you want to configure your client while the server is initializing. And now you can create the new event loop, because why not? And doesn't harm. You're gonna have separate event loop groups for server, and different event loop group for the client. And if something happens, you should be in general good, but doesn't actually matter here. And if I share this client with the pipeline, now you can see we have server event loop group, two threads two event loops that are that are executing the pipelines for each connection, and now we have the new pipeline of the client. So, and because the communication is not blocking, you need to await somehow for response in order to resume the caller's pipeline. And this example, handler C, right? So my question is, which thread is executing handler C? And I don't know if anyone would like to guess, but the answer, it depends. And you have two options. You have access to the callers, to the server, to this channel context I showed you before, and you can simply call the API on the context, and netty will realize that is on the client's thread and not on the caller's pipeline thread, and will just push the task to the other event loop, and you're fine. You're good. But maybe you're not that lucky, and maybe you would like to use CompletableFuture because it's a good, utility, good way to for synchronizing to threads. But maybe you're using then apply, and you're actually not stating what thread will be executing those the replies from the downstream services, and maybe you should use this API and specify exactly which executor you want to use, which executor should be applied to deal with the response. And again, probably you want to just use the event loop of the callers channel, but we know that we don't have access to it, right? And for all those years, we never realized, because probably the logic in this handler C was very simple, and we were lucky, and we were. But at some point there was too many calls, too many downstream service, and maybe we changed the logic at some point in the server pipeline, and we realized that the bottleneck is not the performance of downstream services. It's just this thread that was supposed to do a very little job of communication, and now we employed it to execute the remaining pipeline of both server connections, right? And so it's not about, this time it's not about synchronization that bites us, but it's a problem of internal microarchitecture, right? And well, netty has these ways of dealing with such problems, like if you use the context right, but I guess it could be, netty could help better, and maybe it's very easy to make some mistakes. But I would like to share some other problems with netty we had during those few years. And first of all, it's very hard to route business events between those handlers. Maybe you want to skip some handlers because it doesn't make sense to execute them, and netty doesn't give you the right tooling for doing that. And maybe the business logic is cluttered with the communication logic, as I showed, because you want to pass the context with you, and so it's not the clean separation unless you do it right. And if you have a lot of handlers, because you want to separate those stages in some nice steps, it can pay back with degradation of performance, because netty is it doesn't enforce any order of those handlers, so it has to look up next handler to execute every time it goes from one to the other, and it can take some time. But the biggest challenge for us, I guess, was that there is no way to save state per request, especially when you're dealing with asynchronous calls, and that was really problematic. And it's because netty is just a communication framework. It's a protocol. You define your own protocol. So usually decoding streams of bytes is a synchronous task, and we should look at netty as a very low library for defining those protocols. And probably our biggest mistakes was at the beginning, that we lacked this opinions, experience how to install netty in the bigger project. So I'm not blaming netty as being bad choice, because I show you that it has great potential, but you really need to understand what you're doing. What are the alternatives that we can use? Probably Akka. Akka is very powerful and general framework, but there are a lot of buts. It's not elegant in pure Java, and we are working with Java. It's hard to understand flow of the events. You have actors, you have events, and it's easy to create loops. It's easy to make an actor receiving more than one event, and you need to really remember by heart what's going on in your application to track some problems. And actors are usually executed on the thread pool unless you configure it differently. And so that's might be good, but might be not good. Probably reactive streams would be something that that we could employ, but reactive streams were added really recently. Aeron, on the other hand, it's I don't know if you ever heard about that, but Aeron is a communication framework similar to netty, but it's even more low level than netty, and there's no pipeline-like logic, there is no handles structure, so you're on your own, and you really need to be very careful what you're doing. It's UDP based, so maybe you don't want to employ it everywhere, but it has very efficient and elegant threading model, and well, you shouldn't treat it different. You know, like you shouldn't use it unless you know what you're doing and only as a communication layer. But we are using it in the in few projects, and it's really good. Vertex probably would be the best fit for us, and it had good abstraction and separation of concerns, and we also are using Vertex in our projects. But it's quite a big framework, and we didn't want to learn everything. We didn't. At the time we didn't need all those features, and maybe applying Vertex force us to rewrite a lot of things from scratch. So I probably could. Continue giving you, speaking about Eric's Java, but Eric's Java is good for transforming and merging some streams, but we are not doing that. And maybe other libraries for interacting between threads, but it doesn't make sense. So after some debate, after it was not easy conversation and decision for us, but we decided to write our own implementation, our own framework. But I don't want to speak about. I don't want to throw a lot of code here and show you, okay, we did that and that was decision here and there. I want to focus now on the rules that I think are important, and I think that's the most beneficial for you. If you ever want to write similar frameworks, maybe you will consider that those rules are very important. First of all, we want to give better structure to our business logic. We wanted to have a reasonable threading model, so now we are not bitten by some problems with how threads are interacting. We wanted to decouple from underlying communication framework, and as a side quest, we wanted to remove some redundancy, and we want to have a better protocol, because the one we were already using was not that flexible, and we couldn't upgrade to new version easily or add more messages to the communication if we wanted. So if you look only on the application logic, I think of the application as a flow of those stages, similar that netty has the same pattern. And so flows should be composed of the stages that transform input to output. But the difference is that I wanted to, if we have a request, I would expect response by going to the end of the flow. and if something happens in the middle, it means it was an error. So I wanted to have predictable termination of the flow, and once the flow is terminated, I must have a valid response. And probably stages should be we should interact with stages by events. And the threading model, I say now the single-threaded pattern which we've chosen, but there are lots of different choices. And for example, you can use thread pools and dispatch some tasks to that thread pools, or maybe some other ways, like I don't know, bind the thread to the request by request key, or maybe bind the thread to the handler, and that's what akka does, right? The actor is just bound to the thread, is always executing on the same thread. So we decided to leverage the netty's aeron thread model because we need to process. We wanted to be as close as possible to those libraries. We didn't want to switch from their model to different from their threads to different threads, and we wanted to reuse this. And as a consequence, we knew that each request will be executed on the same thread always, and if we have some asynchronous job, we make sure that we get back to the thread that initiate the call, and by that we were able to simplify our logic because there was no synchronization. We were able to write very simple and powerful circuit breaker implementation, message correlators, and I don't know, message load balancer for our for orchestrating the requests and responses. So that's very basic implementation. You will imagine that it took us, I don't know, weeks or months to do that. No, it's only a few days because we don't have to deal with other threads with synchronization and stuff like Histrix does. And when we checked the flame graphs, Histrix were everywhere. You know, like and after switching to our own implementation, there was almost no problem in that area, at least. But the only problem I see is when you have a single thread pattern, you cannot share anything between threads, right? So you have to duplicate those objects with states, and as a result, we have more connection from bidder, for example, to the downstream services, or from traffics to bidders. So I present you a Stardust, and I commit first some code in late 2016 because I was bored, and later my colleague stepped in and he did the hard stuff. So the protocol and communication is one thing, but I think the most important is those rules that we wanted to enforce on the users. That's why Engine was introduced, and Engine deals with dispatching events to the same thread. Only Engine knows about thread and flow of stages. And thread, there is at least one engine per thread, because if you know that you're gonna create one flow and then you maybe want to change your mind, it's better to have an additional logic. Maybe it's better to construct the other flow and reason about how the flow is executed. You don't want at the middle of the flow make some if statement and then do some logic to reroute your business logic to other handlers. You would like to have many flows, and because of that, maybe you want to have many engines. Stages know about the business logic. Only way to interact with stage is through events. one event can visit same stage only once, and stage can accept only one type of event. And as you can see, a stage is more or less like in netty a handler, and we have the we define input event and the output event, and we have the context. But this time the context is only some metadata that it's created per request, and it always goes with you, so you can save some information that you wish, or maybe you would like to pull some service that is only created for this request. So request now is transformed to for example, active campaign event, or maybe you want to decide that you don't want to bid, and that's your exit from the flow. If you we introduced the asynchronous hierarchy of the, so there's like a alternative of for the handler, and we are returning here not event but a receivable of the event, and you may be wondering was the receivable, and so it's just another implementation of the promise, but we didn't want to allow people to. We have many. There is features from Java. There is features from Guava, from Scala, from RxJava, and we wanted to have a simple abstraction over those and only allow the right usage of those features, and that's why we have receivable. In configuration, it does look like something like that. You see that's all those stages, and that bidder need to execute before deciding that it can bid. And we are actually compiling in the runtime when the server is starting that we have the right components, that the handler is getting the right events, and so on and so on. So we can catch some problems here. So in conclusion, we are providing the standard implementation of netty clients and server, and the same goes for aeron. And that includes metrics, load balancers, circuit breakers, and if we want to change something in the future, we have this clear separation of the communication logic and the business logic that is run by the engine. And very important stuff, we provide also the standard implementation of the server mock, and that speed up our IT testing. If you are a developer, you just grab the Stardust library, you configuring it with whatever you want, and that's it. You don't have to think about I/O communication anymore. So right threading model is a key because our max round trips times has stabilized. It's not that they are lower than before, but I will show you now that this is 7 days. This is a screenshot from our production, and those are max times. So you can see that we are way below 100 milliseconds, and we are like around 50 milliseconds. If we zoom in, it clearly shows that it's 50 milliseconds, and we have an additional 50 milliseconds to this maximum latency that we can work with of 100 milliseconds. And if we look at the 999s percentile, we see that it's 10 milliseconds, so it's even better. And 999s, we are around 5, but below 5 milliseconds. So maybe there was something with scaling, or I don't know. But you see that we're still good. So additionally to that, we don't see any timeouts. We don't see any fluid problems. We don't see any back pressure, or the circuit breakers are not kicking in most of the time. So again, we had 20 machines in one availability zone, and now we have 4. And our traffic increased from 80 in 2015 to 150,000 requests per second in 2016. And we can handle this only with few machines. And we managed to spot and remove mistakes in our code because now the code can be simple. And there's no synchronization, and actually we just focus on the logic in the thread, and we in the handler, and then we compose those flows from handlers, and it's easy to change something, the order, or remove, and nobody cares what other handlers are doing because we have this good separation. But we can still reason about the whole flow. It's easy to understand that if something happened, we know what happened before and what should happen later. And probably the configuration of the Stardust is not foolproof. I didn't want to get to the details because it would probably it would take time. But I think we could work more on that. And as a big win, we are not depending on any framework anymore, and we can switch underlying communication framework easily, and it just works for us, right? So we are in the control of flow and resources. If we want to add another additional downstream service, we can do it, and that would be that big cost for us. And that's only with almost 300 lines of code. So it's I think we spend more on rewriting our code to this new model rather than like fighting the code. It was just very straightforward, and the whole implementation of this framework is very, very simple. So takeaways: I think you should first understand the problem, and then look around, see what are the alternatives, how they are doing things, why they decided to what's the philosophy of each framework library, and see if it works for you or not. And then I think you should always choose the right microarchitecture, because people are talking about the microservices, that you should use Docker, but nobody tells you that there are still threads in your machine, and you have multi-cores on those machines, and sometimes you're going to be I/O bound. You're going to dispatch many calls to upstream, downstream services, but sometimes you will have just maybe offline processing. So maybe it doesn't matter that much, and maybe you want to just to focus on your thread pool and just feed it with some work. And I think you should focus on your business, because your team will grow, people will come and go, and it's not that easy to share all the information why this and that decision was made, and it's very easy to introduce problems because you think you're doing right, but nobody checks you. It's very even though you have you have some conversation with your colleagues, you're doing your best, you're performing some reviews, then it's easy to make a mistake. So that's it. I hope I convinced you a bit, and if you want to ask some question, you can do it now, or we can meet later. Are there any questions? Okay, so thank you very much.